change is one of the biggest challenges facing the world today. The impacts of climate change affect all of us. They're global and they have the potential of being extremely devastating, ranging from the rising sea levels, which cause issues with flooding and loss of value of coastal properties. We're going to see more extreme weather, more intense droughts, things of that nature, which will impact agriculture, food and water supply. Just the whole range of impacts are extremely devastating and things that we need to start working now to head off. So Cornell is pursuing solar energy as a part of our climate action plan. Back in 2007, President Skorton committed the university to completely eliminating greenhouse gas emissions from campus operations. So there's a whole range of activities that we're pursuing around generating more renewable energy with technologies such as solar, wind, geothermal, hydroelectricity. A lot of people think that solar energy doesn't make sense in upstate New York. That's just not true. We actually get a lot more solar irradiance, it's called, than, for example, Germany, who's the world leader in solar production. Just as a point of context, enough solar energy, sunlight, hits the planet in 1 hour to supply the world's entire energy needs for a year. And it only takes a few fractions of a second for enough sunlight to hit the planet to supply Cornell's needs for 1 year. So our challenge is figuring out how to capture it efficiently and store it for those times when the sun is not shining.
We were really excited when we were presented with the opportunity to help Cornell University achieve their sustainability goals. We worked with a team from Building Energy and from Distributed Sun to design a project that was approximately 2 megawatts, which met the requirements of NYSERDA's incentive program and allowed us to ultimately sell electricity to Cornell University at a price that was equal to or less than what they were paying for electricity from the grid. Not only was the downstream effect positive in terms of the fact that it reduced the carbon emission, but it also had a positive financial outcome for Cornell and allowed all the stakeholders in the project to achieve their project profitability and sustainability goals. Once we completed our due diligence, we determined that we had a very specific price point that we needed to hit for the major pieces of equipment, and we also determined that we had a very fixed amount of peak power that we had to create on a very limited amount of space.
The solar farm that we constructed at Snyder Road is covering an area about equivalent to 10 acres. And within the fenced area, we have a huge number of solar panels that are all connected together and provide DC direct current electricity to what's called an inverter. All the things that we use in society, we've got to provide alternating current. So after the solar panels have made electricity in a DC form, it then goes into an inverter, which converts it to alternating current. And that electricity is now ready to go into the grid and provide energy wherever the grid is connected to load.
This solar field was designed on an 11-acre lot, and after a geotechnical survey and further site analysis, we found that we lost about 2.5 acres because of protected wetland, leaving us with about 8.5 acres to work with, still having to meet those same design requirements.
This created a challenge because power density of solar modules is very rigid and very limited. You can only produce so much power with so much space. So we had to think very deeply about how to solve that problem. The 3 major pieces of equipment in every solar project are the module, the inverter, and the racking system.
Every panel has a different power. On the market we can find 300 watt, 305 watt, 310 watt. We need to find obviously the best panel that we can find on the market. And what the panel do is convert the energy, the solar energy, in energy that we can use for our machine, for our supply, or what we have in our home.
Not a lot of people know what an inverter is, but basically an inverter is a piece of equipment that turns the electricity that's created by the module into a type of electricity that can be used in the grid and transported and distributed somewhere else. And of course the racking system is the metal frame upon which the module sits. So for this project we had a price limitation of $1.18 per watt for the 3 major pieces of equipment, and we needed to get 2 megawatts peak of solar on 8.5 acres of buildable space. Your challenge is to take the information that's been given to you and determine, first of all, if the project's feasible at all. Can we get 2 megawatts of power on that amount of space? And if we can, is the price for the equipment that we've been quoted low enough for us to achieve our financial goals? Also, please remember that this is a 30-year project. This equipment needs to be on the site and in good operating condition for a 30-year period. So quality is important. Good luck. There are multiple ways that this problem probably could have been solved, but given market conditions, the availability of equipment, the cost of the equipment, and the technological efficiency of the equipment, we ended up with a very unique solution that we felt like met all of the project stakeholders' goals and objectives.
We selected 7,600 panels, 305 watt peak for our project because they were available on the market for the right price. 300 is very low value for our project, and 310, they are very expensive, and for our project we need to find the best solution in terms of nominal power.
We were able to determine that the 305 watt modules combined with inverter A with the racking solution that we provided to you guys not only met our price thresholds that we had to meet, but it also allowed us to produce the 2 megawatts of peak power that was required to meet Cornell's needs as well as the requirements of the state solar incentive. We didn't select inverter B because we felt like inverter A was a higher quality piece of equipment. Remember, this was a 30-year project. Not just 30 years of time in a good kind of weather conditions. This is 30 years in upstate New York where weather can reach pretty extreme conditions and there's lots of snowfall. Inverters are oftentimes the most common piece of equipment that has shortcomings and failures and can be the number1 leading cause of not creating as much power as you had projected or to even catastrophically have a complete shutdown and not produce any power at all. So we selected inverter A because we felt like it gave us the best chance of high quality performance for the entire duration of the project.
The first time you start on any time you start out on a new project, like Cornell's commitment towards a more significant contribution of solar energy to the energy portfolio that we have now, always brings with a few lessons learned. In this case, I think there are interesting lessons learned with regards to the utilization of this system during summer and winter months. So in the winter month in Ithaca, you have a challenge unique to upstate New York in that many of the panels are going to be covered in snow. So in that case, the energy harvesting there is really focused during the summer. Another interesting lesson learned is that we can actually utilize the farm not just as a resource to generate renewable energy, but also as a teaching tool that we can take students out there and show them this is what a solar farm looks like, this is how they operate, and they can actually manipulate the modules a little bit and see how, for example, how shading impacts the output of the solar cell. So as an educational tool, I think that's a really interesting lesson learned moving forward, and how you can actually also use it as an outreach and communication tool to show the broader public how these farms actually operate and what their role is in our future energy portfolio.
As you've noted, there are a diverse set of skills and expertise that are required to pull a solar project together. Today, you've heard from an engineer, a project developer, which is kind of a financier. You've heard from a construction manager, and you've even heard from some company executives. Now, we'd like to introduce you to each of these guys individually and let them tell you a little bit about their background.
My name is Joshua Swafford. I'm a construction superintendent for ABM. I got into the solar field mainly for the interest of learning the technology and growing with a newer venture company in the solar industry. I take a point of view from the ground level. Once the construction phase actually begins, I'm actually feet in the trenches, seeing the daily installation of all the works and activities that are done from the subcontractor level all the way down to, or all the way up to the project management level. The liaison between the actual site activities and the shareholders. My background is where I went to school is actually DeVry University in Phoenix, Arizona, where I graduated with a Bachelor's of Science in Business Administration with a focus in project management. I've always been interested in projects, seeing from the initial start phase all the way up to the final completion. And what's most gratifying from all of that is seeing a smile on the customer's face, feeling a sense of achievement and actually completing the works, having a hand in pretty much every phase of the project cycle. Project management is pretty much my life. It has a lot of, it forces you to be flexible in both your time and your energy, but from that experience, you're more malleable from the different industries you can get in. Once you understand the basis of project management, and especially in the solar field, where there's several parties involved, there's several both contractors, business administrators, all the way up to shareholders and tax equity investors, for instance, that need to have concise and clear understanding of what's going on site, and feeling that sense of empowerment and ability to actually deliver that information is very important to me.
My name is Francesco Miselli, and following the design of the project, I have a background based on engineering basis and obviously a general understanding of solar, the sun, and everything is related for around the sun. And engineering is very helpful for find the method and the process for design a power plant, but obviously you need to have a green mind for follow this market.
My name's Ted O'Shea. I'm the Vice President of Energy at ABM. My job as an executive is to determine the financial viability of not just a project, but an overall business. As such, I've got a lot of experience and time analyzing financial models, building budgets, and determining if the things that we're selecting to do are actually going to work and make a profit in the long run. So I think it's critically important from my perspective that if you can understand a financial statement and you can understand how the different pieces of it come together, and if you've ever studied it, that's an income statement, a cash flow statement, and a balance sheet. If you can understand how finance works, there are a lot of different businesses that you can potentially run. In fact, a lot of times people say that a business is just a widget. If you really understand the fundamentals of business and finance, there are a lot of different types of businesses that you can run. So if you can combine the core functions of a STEM education and have a strong accounting and finance background, the potential job opportunities or even businesses that you could start in the future are almost limitless.
I came to Cornell in 2007 and was really inspired by the resources that are here with developing new materials specifically for renewable energy technologies. And we're still heavily involved in that, both for solar photovoltaics as well as for energy storage technology. So it's a really exciting place in that regard. And also in working with the students here, they're really top-notch students that really understand the significance of both the technology towards renewable energies moving forward as well as deployment and actual implementation. As far going back to undergrad, I've always been interested in both the scientific aspects of physics and chemistry, but also from an applied perspective as to how can you apply that knowledge towards something useful. So that's why that was the key motivation towards studying chemical engineering, that you can have both an insight on interesting science and advances on the scientific side as well as the actual application thereof. So that's why I studied chemical engineering in undergrad and also for my PhD. For the PhD research, I've worked on nanostructured materials and learned a lot about how could you make materials with unprecedented control over size, shape, and properties. But the key thing that really excited me about this is how could you do something useful with that knowledge. So other than showing that you can make materials with controlled size or shape, what useful devices or what useful technology could you develop from that? So that aside, yeah, that was a key motivation for getting into renewable energy technologies at that point. Is you have an interesting material system to work with. You can do good things with it. What would be the best good thing you can do with that?
So I got interested in sustainability, environmental issues in high school. I did not imagine myself building solar farms later in my career, but that's where things led me. I just knew that I had an interest in helping address environmental and sustainability issues. So I would recommend to those students and folks out there that have an interest to get an education in the particular area that interests you, whether it's the science, the technology, the engineering. There's a huge role for the social sciences as well, communications, helping folks understand the impacts of their behaviors and ways to change their behaviors and adopt more climate-smart behaviors. As we've seen through this solar farm project, the financial aspect, figuring out how to finance these projects, leverages subsidies and funding that are available, putting together the whole package for the 30-year lifetime of the contract. Also a role for those interested in the legal profession. So I would just encourage students to embrace their passion, and whatever their particular skill set is, there's a role for everyone in helping to address climate change.
My strongest recommendation for anyone that's interested in the renewable energy field is that they get really strong math and science skills. And physics is really important. It's your friend in energy, and if you don't know what you're talking about, the physics will immediately get in your way. So the strong foundation that I received in college in math and physics has been very helpful in making sure that I make the right technical decisions. In addition, you have to make sure that you can communicate, you can partner, you can write, and you can present, because if you're going to try to do things differently, you're going to push the envelope and you're going to cause people to be uncomfortable because you're trying to do things that are different, and they will have a different impact that people aren't used to. Solar energy, as an example, takes a lot of surface area. So using a large area like we did for the Snyder Road farm, 10 acres, some people would argue that that's an improper use of land, that we should do other things. We shouldn't cover it up with solar panels. The alternatives, though, based on fossil fuels, have such a greater impact. You have to figure out the balance. And overall, we just need to provide the energy needs with significantly less impact, and solar can do that.